Welcome back to this fourth in the series of Statistical Experimental Design vignettes. So far, you have become aware of the importance of using the structured plan of attack on opportunities for quality and productivity improvement as we looked at the philosophy of experimental design. In the last segment, we saw how organization for experimentation focuses our prior information to help select the factors and identify the responses for the experiment. In segment 2, we saw how the balanced factorial design is superior to the intuitive one factor at a time approach. Now, in this segment, we'll learn how to formally construct these balanced two-level experimental structures. My monk friend has his saw ready. Let's get our tools out and build these designs. First, the designation of these balanced two-level designs is 2 to the power of k, where 2 is the number of levels and k are the number of factors. If you're worried about more than only 2 levels, we'll cover this aspect of experimental design in a later vignette. However, from an efficiency, remember, getting the required information at the least expenditure of resources, from that point of view, these two-level designs are nearly perfect. You may call the runs experimental trials, but the farmers who invented experimental design call the individual runs in an experiment treatment combinations, since it was the way each trial in their experiment treated the combination of factors and levels. The number of treatment combinations is simply 2 to the power of k. Frank Yates was one of the researchers at the Rothamsted Agricultural Station in England, and he devised the standard order for setting up an experiment. It was named after him, Yates Order. Each column in the matrix, these are sometimes called matrix designs, is a factor, and each row is a treatment combination, abbreviated TC. We build the design column-wise, setting up patterns of minus and plus signs depending on the column number. We always begin with the minus sign set, and we determine the number of like signs per set using the rule 2 to the n minus 1, where n is the column number. For example, in column 1, we have 2 to the 1 minus 1, which is 2 to the 0, and anything to the 0 power is 1. So the pattern is to have 1 minus and 1 plus per set in the first column. In column 2, we have 2 to the first power, which is 2, and we have 2 minuses and 2 pluses in the second column. Column 3 has sets of 4 minuses and 4 pluses. Here's an example for a 3-factor experiment. For the generic design, we label the factors in alphabetical order, A, B, C. Notice the patterns of the sets of minus and plus. We always know when to stop by the total number of rows in the matrix, which is 2 to the k, where k in this case is 3, so we have 8 total rows. While we name the column factor headings with uppercase letters, we name the rows with lowercase. These unique row headings are called treatment combination identifiers, and they come in handy when we are actually executing the experimental runs. The column heading letter is brought to the row heading when we have a plus sign match. Watch. Let's add some real factors from the image quality experiment for which we wrote a goal and an objective in the first vignette. We have the Elon developer in the A column, the hydroquinone developer in the B column, and the temperature of the development in the C column. We have inserted actual levels of these factors in place of the minus and plus signs. Since we would not want to superimpose any other systematic effects on this set of factors, we will run the experiment in a random order, which is the run column on the far left. Since most people in science and engineering are very systematic, They would probably begin at the top of the matrix and go down to the bottom. So to make sure the experiment is executed in random order, we reorder the matrix with the first run at the top followed by the second and so forth. Notice the TCIDs make good labels rather than mere numbers that could be confused between the question of, is it the standard run number or a random run number? Some computer programs have this confusion built in, and I recommend adding a column of TCIDs to prevent this logistics error that could spoil the experiment. You should try out experimental design building with a very simple two-factor investigation. A PDF file with a description of the factors and a template for building the TCs was attached to the email announcing this vignette. If you are watching on YouTube, you can send me an email at tbbeqa@mac.com and I'll send the description and templates to you. Here is the description of this helicopter experiment. The idea is to find the combination of wing length and width that maximizes descent time. You should write a goal and an objective. Remember, the objective is formal and is in the form of to test the hypothesis that a response is a function of, name the factors. The template shows the lengths and widths. Fill in the physical levels and the TCIDs. Cut out the helicopters and drop them using a stopwatch to get the descent times. Here is the helicopter template. Cut on the solid lines and fold on the dashed lines. The nose, at the bottom, gets folded in to make a weight at that bottom. Bend the wings at a 45-degree angle. As you run the experiment, you might think of other factors that could influence the descent time. Brainstorm these other factors so you can discover more inclusive functions in future experiments. You have learned how to set up balanced two-level factorial designs. Our next vignette will show how to build fractional factorial designs, which are the workhorse designs in statistical experimental design. See you then.